Do 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 do. All right, I have everybody's mission 4. I say I got a stack of something up here. Thank you. All right. So I'm a little bit behind. So my my solution is sadly not complete, but I do have many solutions posted, so we can look at those. And of course, if you guys have questions, we can try to answer those. Once I get this thing plugged in, I'll begin with a word of prayer here. You guys ready for the test? Ready? Oh, no. Take it right now? All right, let me go print it out. Let's do it. No? Okay, just kidding. All right. Dear Father, we thank you for this day. Again, I thank you for this class, and it's time we have to meet together and study your creation. Let's pray you be glorified in what we do, and that we all understand a little bit more about differential equations today, Lord. In your name I pray, Lord Jesus. Amen. All right. See if I can get this thing working. Come on. Why you turn off? All righty. So I hope you guys understand the Laplace transform a little bit better now. There really is no substitute for just trying it, you know? Yes, sir?
I saw you put an announcement out that you said you graded mission 3, but my grade is still not that good.
Huh. That's interesting. Well, maybe there's a no name. It could be that's your name. That's one possibility. So I'll have to look into it. But the mission 3s, they're in my office sitting on the floor. We can go after class. So like problem 73, there it was just kind of get that out of our system to start with. So here the question was, are these conservative vector fields? Of course, conservative vector field is not just a formula, it's a domain, right? To say it's conservative means that there exists a potential energy function whose negative gradient matches the given force on the domain. And that is in fact the case for parts A, B, and C. Respectively, this, and this, if you take the gradient, slap a minus on them, it gives you back this force, and that force, all right? Now, I have not belabored the point of how you calculate those. Hopefully you already know about that. That's the calculus 3 thing. We look for the x derivative to match the x component, the y derivative to match the y component. We integrate both and try to, find a function that solves all of those conditions at once. But part D is a little bit tricky. That one's not conservative, even though it's the same formula, right? Same formula, but the difference is domain, right? This is the half plane. And on the half plane, you do indeed have an inverse tangent y over x, which differentiates to give back to that. The thing is, I can't define an angle function on the totality of the punctured plane. And let me skip ahead a bit for a second here. So like the reason for that is simple enough. I think I did this in class. Maybe anyway, I don't remember. I did. I'm teaching too many similar classes this semester. It's all bleeding together for me at this point. But if I parameterize the unit circle and I calculate the line integral of that vector field around the unit circle, I get 2 pi. So if that's the case, it cannot be the case that this is conservative on the punctured plane, which includes the unit circle. See, because if it was, then we'd be able to integrate, around the loop, around the circle, and we could use the fundamental theorem of calculus, and we just get 0. But it's not 0, it's 2 pi, right? So it's not possible to find a potential function on the totality of the punctured plane. Now, this is a little bit disconcerting because you might be like, wait a minute. So they have the same formula, but this one's conservative, but the other one's not. So how do I know? Right? Because if you check the closed condition, they both satisfy the closed condition. So, I mean, I don't know what to tell you. It's tricky, you know? But the good news is, this is pretty much the only example in the puncture plane, more or less up to a change of notation, that you can come up with that's like this. So, anyway, all right. So that let us solve 74, right? Because it was the same formulas, like was this exact equation, and I just wrote down minus the potential energy equal to a constant for the solution. That makes sense, you see, because if the force is conservative, right, for the PQ force, that means that the total differential of minus the gradient is PdX plus Qdy. But that means that u equals to, like minus u equal to c, is going to be a level curve which solves this exact differential equation. So there's this one-to-one correspondence between finding conservative, finding the potential energy for a conservative force and solving in a corresponding exact equation. Likewise for part B, just like that. All right. Now, problem 75. I say see problem sheet. That's not quite true yet. More on that in a minute here. Problem 76. We're supposed to find the integral curves parametrically, which means we have to solve this, two differential equations. They're intertwangled. This is a linear system, right? We talked about how to solve these, right? The matrix problem, and this one, I can just write down the answer. Like it's eigenvalue 3, and for this guy, E1 and E2 are E1's an eigenvector and E2 is a generalized eigenvector for order 2, and I know how that goes. That means it gives me the eigensolution and like this kind of generalized eigensolution, right? I get the E2 plus TE1 when I feed it to the magic formula. And then, of course, if I go back and write that out, that gives me the path C1 e to the 3t plus C2t e to the 3t and C2 e to the 3t. All right, great. That's part A. Now, part B was this. I was trying to integral curves for 2x plus y, x plus 2y. And this one, I'm up against this system. So I write down my handy-dandy matrix, find the eigenvalues are 1 and 3. And so if you look at a minus I, or if you look at a minus 3i, you can just look at these things and say, oh, well, the eigenvector is minus 1, 1, and the eigenvector is 1, 1, right? Like, it's pretty clear. This vector times that gives me 0, and this vector times that gives me 0. So respectively, these are the eigenvectors, v1 and v2 for eigenvalues 1 and 3. Once I know that, I can write down the eigensolutions per our usual method, and that gives me, c1 e to the t times that plus c2 e to the 3t times that, which gives me this parameterization of the integral curve to the vector field. All right? Now on to part C. So part C, same song and dance, but this time we have an eigenvalue which is imaginary. So we find a complex eigenvector of 1i that gives us a complex eigensolution, which of course then we take the real and the imaginary parts of to construct our parameterization of the integral curve. All right? Now, I know what's good for me, so I skipped to part C because I'm out of time. So I know full well there is no prayer. I have no prayer for doing parts A and B today because I don't have 4 hours to sit and tinker, which is what it's going to take me to do A and B. I just know it. So I skipped part C because I realize the limitations of my day. And so then I'm trying to find the Cartesian form of the integral curve. So I use the usual trick. Dx dt is dy dt over dx dt, which is q over p here. And so I'm solving this, which gives me that, which straight away integrates to x squared plus y squared equals to r squared. So that's the solution to the the integral, the Cartesian form of the integral curve differential equation. Now the question is, how does this relate to my parametric integral curve that I found in part C of the previous problem, right? So I thought it would be good for us to look at this because this is the one which is like, this would be like, for sure, parts B and parts A are not reasonable test questions, right? But part C would, in principle, not be insane to test you guys on because it's not too bad. So how do you check if the previous solution actually parameterizes the curve? Well, you plug it in and see if it works, right? So I have x equals to this, y equals to that. I plug them in, add their squares, square it out, right? Notice I get this plus. Yeah.
Yeah, it's raining cats and dogs out there.
Yeah, it's something. So I get these two terms, they'd be canceling, right? Same terms, plus, minus. And on the outside, you get a cosine squared and a sine squared cosine squared. Those add to 1, and we get c1 squared plus c2 squared is equal to r squared. And so, in fact, yes, we do parameterize this with the previous solution. And the relation between the r, which of course is the radius of the circle, and the constants is that like the constant squared plus the constant squared is equal to r squared. Or there's some sort of like kinesthetics class up there or something, like they do in jumping jacks. Like what's going on? Like, good grief. All right, I digress. Problem 79. This one, we had to calculate the Laplace transform of sine 2t and cosine 3t, right? So you guys have a formula sheet, right? And I would encourage you to use my new and improved, well, we'll look at that in a second here, but my new improved sheet, which I don't think I printed out for you, I'm sorry, but you know. But I did give you the, like 4 different formats. I give you PDF, the LaTeX source, and the doc file where I cut and paste things into one sheet. Like you have all of the possible options. You can make it your own. You can add formulas that you like. You can take examples from my notes and shrink them down and put them on your sheet. Like it's all possible. Yeah.
So we can bring that into a test and edit it as we see fit?
Yes.
Sweet.
Yeah. So rather than just giving you the sheet that I've copied for like 5 years or so and about 20 copies, as you can see, it's degrading, right? Let's forget about that sheet. That sheet is dead to us. Let's use the new one. You use what you want. My point to you is you may bring a page of notes to the third test, all right? I think, personally, that page of notes should include my new and improved Laplace formula sheet, but if you don't use it, I'll just be personally offended. So, but no one cares about that, so it's fine. Anyway, so we got, yep.
Do you mean bring it to test 2, the sheet of notes?
Are we having test 2 or test 3?
Test 2.
Oh, man. Like I said, I'm teaching a lot of classes this semester. Yes, let's make it test 2. That would make more sense. Thank you. So I haven't tested you guys on systems of differential equations yet, huh? I better put those on the test, right? Yeah. Don't worry, I'm going to take a look at missions 3 and 4 before I make this test. Don't worry. So this is sine of 5t and sine of t after we use the imaginary exponential. Now, of course, you don't have to do this. You could simply write on your formula sheet the product identity. Like sine of a times cosine of b is 1/2 sine of a plus b minus the sine of a minus b. No, wait, is it? Minus the sine of a plus b. I don't know, whatever that works out to. Yeah? And then you could just apply that identity to this problem. That'd be fine. I personally just like to derive everything with imaginary exponentials because it's kind of my one size fits all. It's a hammer. Everything looks like a nail with this thing. Like, it's fine. So anyway, this is that with linearity of the Laplace transform. And so there you go. That's the Laplace transform. If I didn't do that, I don't begin to know where to start. All right? Like trigonometry matters. Let me go back to the sheet. All right, so we'll look at that in a second. I have posted, like, in addition to this, I've posted 3 other things, and those 3 other things have many of the problems I haven't solved on those. So if you hunt around in these 4 PDFs I'm posting, you'll see most of the solutions to most of the problems that you just turned in, all right? But I will try to finish the current solution and make it pretty and stuff, hopefully tonight. So hopefully I'll have that posted tomorrow. I'm not there today at the moment. We already talked about this. I'm punting on part A and B for now. Some of these we can just straight do, right? Like the Laplace transform of t squared e to the minus t is like that. To show you where I'm getting that, let me see if I got it open. Just a second here. All right, so like, see this guy right here? The Laplace transform of e to the at t to the n. So if I've got, you know, whatever I had, I'm using this one for that, all right? It's just a matter of identifying what we're up against. Oops. See, I've got t squared e to the minus t. E to the minus t means my a is minus 1. Excuse me, yeah, a is equal to 1 rather. So that's why I have, maybe that, oh, I have a moment of doubt. No, it's okay, it's okay. So as a general point of order, something that can keep you on the straight path, think about this. The algebra you've already seen before, right? If our characteristic equation has a root which is lambda equals to 1, right? Rather, lambda equals to minus 1, right? That would be e to the minus t. That would come from a lambda equals to minus 1. What's the characteristic equation? That had to come from a lambda plus 1 equal to 0, right? Whatever you're putting here, remember, that is exactly what appears in the process of the Laplace transform corresponding to that 0. So if you think about this correspondence between the characteristic equation and the solutions that you already know, you can kind of check yourself on signs as you do it. So that's why I knew, like, I'm okay to have, I have a minus here, I've got a plus 1 here, because I know that, like, at the end of the day, this would have come from like a characteristic equation, lambda plus 1 cubed. Also, that's also another point of order. You know, like in the homogeneous solution, how would you get a t squared e to the minus t? Well, that has to be from at least a third order problem, right? Because you're talking about e to the minus t, t e to the minus t, and then third, t squared e to the minus t. That's how they go, right? So I had to have a third order problem in order for this to appear in the solution set. So it makes sense that I've got a cubic down here. But anyway, of course, you can just follow the rules on the sheet as well, you know? Okay, I shut up. We just talked about this already, right? Trigonometry. The next one, I foolishly decided to squeeze into the problem sheet. Don't do this. But what does it matter? We're done, right? There's no more problem sheets. There's just quiz 5, which will be not as bad. Quiz 5? Homework 5. What is it called? Mission 5? Did I call it quiz 5? Yeah. For the purpose of today's lecture, let's set mission equal to quiz, equal to homework, equal to test, equal to, well, just all of the terms. Let me shut up. So, whoa. So look here, guys. There's this t. Remember, t in the time domain is minus the derivative in the s domain. So all I do, well, first of all, I've got this pesky sine of 2t plus 3. I must know my trigonometry, so that gives me cosine 3 sine 2t, sine 3 cosine 2t. And then I have to differentiate, because I got this t here. The Laplace transform of e to the t sine 2t is 2 over s minus 1 squared plus 4. The Laplace transform of e to the t cosine 2t is s minus 1 times s minus, divided by s minus 1 squared plus 4. And so that's why I did that, all right? And then you differentiate, and it becomes this, which maybe we could clean up, but I'm leaving it like that. The next one down here is much simpler, right? I mean, we just look at it and go, oh, well, that's 6. So this is the 6 rides along. If we have the t to the s to the 4th power, we divide by 4 minus 1, which is 3 factorial. And that's an e to the t cubed, which simplifies to t cubed e to the t. Hooray. This one, cosine 2t. Did I do something? What did I do? Oh no, what have I done? Ah! That's a corner, you know? An evil corner. They should have like a rubber bumper on this or something. You think it's a sine 2t. Are you willing to bet a letter grade on that? Good choice. Yes, that should be sine 2t. Yeah, sorry about that.
Go up a letter grade?
Well, it only works against you. It's not like, yeah. It's one of those heads I win, tails you lose sorts of situations. If you do that with a 4-year-old, even a really smart 4-year-old, you can make it work for a while. Like, when my son was about 4, we were like at a Dunkin' Donuts somewhere. I'm like, all right, Daniel, you ready? Heads, I win, tails, you lose. Like, I flip the coin. I'm like, heads, oh, I win. Are you ready? Let's go again. Heads, I win, tails, you lose. Flip, tails, oh, you lose. All right, you ready? Let's go again. Heads, I win, tails, you lose. Flip, heads, I win. Yeah, it's fun. This is why you should have children, so that you can mess with them, you know? Like, what if you taught your children that red was blue and blue was red? Wouldn't that be fun? Or how about you train them like scissors and forks, like just exchange the meaning of the words. And just wait for them to enter society and deal with other people. It'd be hilarious.
No.
No?
You said gaslight his children to being colorblind.
No, that's green.
Somebody should write a book in like, you know, like a very flowery children's book style, like children and gaslighting children or something like that. Yeah, with all the requisite proper art.
No, that's red.
Let's see here. So,
Guess I'm colorblind.
is this one okay? Oh, look, so I got an S upstairs, so I get a cosine. I seem to have learned it now. Great. It's so sad, like the easier problem I get wrong, of course.
It looked at you funny seeing you.
Oh well, anyway. 1/24th t to the 4th. Let's go on here. Problem 85, you might have found interesting. I found it interesting. So you will remember, or perhaps be reminded, that the derivative of inverse tangent is 1 over 1 plus x squared, which upon the geometric series is the sum n equals 0 to infinity of minus x squared to the power n, which we can simplify to minus 1 to the n, x to the 2n. And then since we differentiated, we undo the differentiation by integration. Integrating this gives me minus 1 to the n over 2n plus 1, x to the 2n plus 1. I don't need to add a constant because the inverse tangent of 0 is 0. So that's how it goes. And then I can take the, so my f of s is actually this, which then I can do term by term inverse Laplace transforming, like so. And it just so happens it works out to something that actually is nice. See, because after you take the inverse transform and use the requisite rule on the sheet that you will print out, you get a 2n plus 1 divided by 2n plus 1 factorial. Well, actually, there's an extra minus 1, so I have to divide by t. The reason I did that was so that I can look at this and go, sine. So sine t over t. Yeah. Anybody else get this?
I didn't do it that way.
Let me ask it a different question. Did ChatGPT get this? No? Yes? Yeah.
You're not supposed to know that.
I've heard the ChatGPT is sometimes helpful, but all right. So this one, these are just answers. Let me skip over to my well, like problem 84, we can look at. So here we just have to do the partial fractions decomposition, which has the form. Oh, come on. Well, that was supposed to be an s cubed. I whited it out, but then there's an s cubed in white there if you look real careful. But yeah, this is how the partial fractions works out. It turns out that there's no 1 over s squared term, and you just have an s cubed, an s, and s minus 2. So when we inverse transform that, we get that. But of course, you guys need to, be ready, willing, and able to do some partial fractioning for sure. Let me show you. So this we've done this in class before, but it's good to talk about again. This is not partial fractions. This is my algebraic sleight of hand for doing the inverse transform when the denominator is irreducible, right? So what we do is, well, first of all, there's a 2 we could factor out, so let's do that. I factored the 2 out. After I do that, I complete the square, and I get an s minus 1 squared plus 4. Hopefully I did that right. I'm somewhat leery about my work now. S minus 1 squared plus 4. Great. Now, once I see that, I'm like, uh-oh, sines and cosines, right? That's what's coming. And shifted, because this s minus 1. So I'm looking at like an e to the t cosine 2t and an e to the t sine 2t type terms. But I have to have an s minus 1 upstairs, and I have to have a 4, well, a 2 upstairs, right, in order to do that. So where does this s minus 1 come from? Well, because I said so, I traded this s for s minus 1. In so doing, I've subtracted 3. But you see I had a minus 15 before, so I got to have a 12 here, because 12 minus minus 12 minus 3 is minus 15. So this and that, they be equal. But this anticipates the inverse transform, namely that this is going to give me 3/2 e to the t cosine 2t, and then over here, because this 2 and that 12, don't forget the 2's out there, so minus 12 over 2 is actually like minus 6 over 2, which is, by the way, minus 3 times 2. I need the 2 to go into the inverse transform of the sign, right? I need that 1, 2 to go to make this the inverse transform of the sign, but the 3 remains, so I get minus 3 e to the t sine 2t. Here is a decent partial fractions. I actually showed some of the work this time. So I set up the partial fractions according to the denominator a over s, b over s minus 1, c over s minus 6, and multiply by the denominator, and then plug in the zeros, and out pops a is equal to minus 3, b is equal to 1, and c is equal to 140 divided by 30, also known as 14/3. And then once you have that, inverse Laplace transform, piece of cake, right? Because this goes to 1/3, that goes to e to the t, and that goes to 14/3 e to the 6t. All right, so that's all she wrote for this part. Now I have posted a couple of other things in Canvas right now for you to look at if you want. Now, if you already understand this stuff, by all means, don't look. I don't care. You won't hurt my feelings. But my apologies, it's a little fuzzy in places. But I think you can read it, more or less. So this is that same trick again. Sine, cosine, there's my sines, And this here, well, that's 1/2 1 minus cosine 6t. So when I'm Laplace transforming, I first must shift to like a sum of regular sines and cosines. And after I do that, I can Laplace transform, right? That's a problem. This one here, another important thing I haven't talked about yet today. You need to know how to convert case-wise defined functions to the unit step function formalism, right? If you haven't pinned this down yet, you need to pin it down. You don't want to try to learn this on the test, right? Learning on the test, not where you want to be, I think. So anyway, once I do that, then we can Laplace transform. Laplace transform of t is 1 over s squared. And this business right here, I have to take e to the minus 2s, and then I take the Laplace transform of this shifted to t plus 2. Now, in order to do that, I have to do trigonometry again, sine 2, cos t, cos 2, sine t, and that, and then we can Laplace transform that. And of course, it picks up this handy-dandy e to the minus 2s term like so, all right? So that's how it goes. Here is a quadratic where the denominator factors, unlike the other one we talked about today, right? If it factors, probably your best bet is just to partial fractions that thing. And if we do that and we work it out, I get 5 and minus 2, which gives me this, at which point we can take the inverse transform. It's like, minus 2 e to the t plus 5 e to the 7t is the inverse transform of that. All right? Now, it is true that you don't have to memorize any of these things because they're all on the sheet. But it is also true that if you really don't know any of them, you will run out of time, right? So there's some kind of balance to be struck there. This is something that, this is kind of like the next tier of studying. Past the initial tier, there's these problems. But you need to get past these because I do test on them. If we have an e to the minus s, e to the minus 2s here, we have to use a theorem which says that, basically this is the thing we use, the inverse, oh man, I'm missing it. There's supposed to be an e to the minus, oh no, it's okay. It's because that up here. So it turns out the inverse transform of this is equal to g, this is the g of t minus 2 times u of t minus 2. That's one of the formulas that's on our beloved formula sheet. If I can go back, I will show you where. See this right here? Where is it? This guy. So to take the inverse transform of e to the minus as times an f of s, what we do is we find the inverse Laplace transform of that, which is little f. We do f of t minus a times u of t minus a. Now I think I The letters were changed. I had like a G in the place of F in the thing we're just looking at, but the principle remains the same, all right? The larger point is that whenever we have, where was I? Oh man. Was here, right? Yeah. Whenever we have an e to the minus as, it's going to give us, back in the time domain, a unit step function shifted to t minus a. All right, so anyway, the trouble here, of course, is that the g of s is this, and it's not altogether clear how you take the inverse transform of that, which means we have to partial fractions. And so the partial fractions here is one we haven't seen yet today, so it's good to talk about, but it is a linear factor times an irreducible quadratic. Why is this irreducible? Well, if I complete the square, I get a plus, right? So that means that this is going to give me sines and cosines in the inverse transform. But in the meantime, this is how I would set up the partial fractions decomposition. Now, usually at some point I have students who, at some point, if you have a good enough memory about calculus 2, you're like, wait, that's not how we set up the partial fractions in calc 2, right? What's this funny business you're doing with this s plus 3 up here? And why is there a 2 there? Can you guys tell me? What are we trying to do? We're trying to take the inverse transform, right? I'm anticipating the next step, which is that I want s plus 3 over this stuff, and I want 2 over this stuff, because the inverse transforms of those, respectively, are e to the minus 3t cosine 2t and e to the minus 3t sine 2t. So I'm just anticipate where we're going, and I just put the s plus 3 here and the 2 here. You don't have to put the 2 there. You could just do the partial fractions and then put the 2 back in by arithmetic later, but why make life hard when you can make it easy? So if you do this way, and we do the algebra, and the algebra here is a little bit troublesome. What I did here was I equated coefficients, which is yet another technique, which is to multiply out and collect coefficients of s squared, s, and the constant, which gives me 3 equations. And the nice thing is that they're kind of nicely solved in the order I wrote them, right? Because we can solve A. Once we know A, we can figure out B. And once we know A and B, we can figure out C. So yeah, it is 3 equations and 3 unknowns, but on the other hand, it's not too bad. And so that gives me my partial fractions decomposition for big G, which then gives me the inverse Laplace transform little g like so. And then finally, I go back to the theorem. I got to shift this guy as appropriate to t minus 2. So I put a t minus 2 in the place of t minus 2 in the place of t minus 2 in the, well, you heard it, place of t. And then, of course, it all gets multiplied by u to the t minus 2. This is how that goes, all right? I'm not going to sugarcoat it. Those are challenging, but you can do them. You're like, how can I do it? Well, I know you can do it. Students dumber than you in the past have done it, right? Yes. Trust me, there have been some very unintelligent people who have passed my class before. It happens. So whatever you think of yourself, think more. I'm sorry, this isn't really an intelligence test. I mean, the question is whether or not you've done the work, right? If you've done the homework and you really understand and you're up to date in your algebra, everything should be okay, I think. Sorry, I'm kind of in a mood today. I had a meeting before this that I do want to talk about it.
Can you talk about it?
I can't talk about it.
You can talk about it a little bit.
Can you
A little
talk about
bit.
it if you change all the names?
Like at least 5 minutes.
No, it's not that thing. It's just
Don't the name drop.
Use metaphors.
use metaphors.
Yeah.
Well, metaphors like I don't know. Like imagine you're a carpenter. You're a carpenter, right? And there's a particular tool you like to use. Not all the time, but every so often. Right? But then one of your bosses tells you, you can't use that tool anymore. Now why? Because like the Campbell County Safety Coordinator said that it wasn't allowed. You're like, well, can I talk to this person? No. But if I tell you, but I can say my concerns about it, and then that will be communicated to this person who made the decision on their lonesome because they're the Wizard of Smart or whatever. That kind of thing. So, It's not a central thing in what I do. It's just something I've used on occasion for some very good students, and it's gotten twisted. Anyway, so here's another good example. If we have this second-order differential equation with initial conditions, we take the Laplace transform, we solve for big Y, we take the inverse, then we do partial fractions to make big Y pretty, we take the inverse transform, solved, right? If there is a unit step function, it's going to get ugly, because this unit step function picks up a 1 over s. And then when you solve for big Y, you end up multiplying 1 over s by the characteristic equation in s, which means you got a cubic, which means you have to partial fractions like this, which we can do, and we will. You probably will on the test. I mean, historically speaking, if you look at the collection of all tests I've given on Laplace transforms, likelihood of there being a cubic inverse transform is like 95%, yeah, something like that, yeah.
What are the odds of there being more than one?
Could happen. So, I mean, I don't think it's a big deal. But anyway, so we find the partial fractions, and then we use that theorem again, and voila. So, yeah. Notice that if there's a unit step function as your inhomogeneous term, we shouldn't be surprised that the solution picks up the same kind of unit step function. The reason being that when the force changes at time 3, the solution will also change at time 3. So we kind of should anticipate there's being some sort of mimicry, if you will, between the forcing function and the solution in this regard. It's not surprising that that happens. Like this problem, I can tell you before we get to the end of it, because there's something funny going on with the force at time 2 and time 4, I expect that my solution will also involve this unit step function and that unit step function. Like that's going to happen. And indeed, after some suffering, it does. So, yeah. Okay, so let me see here. Here's the old spring. You have a spring mass problem. It oscillates one-dimensionally. I give initial conditions. I say, is it possible to strike the mass spring with a hammer such that the system is motionless after the strike? So we're going to assume that we give it an impulse, J naught hammer strike at time A. Can I find a J naught and A to make it such that x of t is equal to 0 for t beyond after time A? Is it possible? So the answer I think is yes, and there's like infinitely many different ways to do it because this is periodic motion. So if you can stop it in one cycle, you can stop it in any cycle, right? There must be an infinity of possible answers if there's one answer. But anyway, so f of t is the impulse with impulse j. I take the Laplace transform, and these are from the initial conditions being 1 and 1. And lo and behold, I get this. Man, the scans are getting worse. And so the inverse transform of this is cosine 2t, and this gives me a 1/2 sine 2t from these two terms. And over here, I pick up a j naught over 2 sine of 2 times t minus a times unit step function t minus a. And then past this point, it's just me quibbling over trigonometry. How can I make it work out to 0 past that time, you know? So, as I say, we don't really care about all this. But so, for example, I can make it happen if I pull j naught equal to the square root of 5, and a is that. So, I don't think I gave this problem to you guys, did I? I did?
I think there's a variation of it on the show.
A variation? So here's another problem. I don't know if I gave this one to you guys or not, but it's worth talking about momentarily. So if I have, like this is one way we could do this. We could use the convolution to calculate the inverse Laplace transform of s squared times s minus a. The other way to do this, which probably would be easier, is just to find the partial fractions decomposition of 1 over s squared times 1 over s minus a, right? It's going to have the form like a over s plus b over s squared plus c over s minus a. I can find the a, b, and c, big A, b, c, and then take the inverse transform. But I think the point of this problem is just to illustrate convolution. So the convolution of this and that, the convolution of 1 over s squared is t. The convolution of the inverse transform of 1 over s minus a is e to the at. I can convolute those to calculate the inverse transform of the product. And after a bit, it works out to this, which tells me, I mean, we could kind of retrospect, figure out what the partial fractions decomposition was. Here's another problem that was, I think this one was actually in your homework, like y prime prime plus y equals a g. Find the solution using Laplace transforms. So if I take the Laplace transform, I get s squared y minus sy0 minus y0 plus y, the Laplace transform of g, which is big G. Divide by, solve for big Y. And then I can take the inverse transform, and I get a y naught cosine t plus y1 sine t. And then the convolution of sine of t with g of t, which says that, hey, this is the integral solution to the problem. And I think I mentioned to you guys before, like this kind of problem, we could also find this same integral solution using like the variation of parameters technique. That would be like another way to derive the same formula if you wanted to. Here we go. This one I did give you guys. This one's pretty nice. So I'm probably just going to let you look at this because if I like print this out and like scan it again, and we don't have a color printer, this will be better than anything else I produce. I'm just going to let you guys look at this one. But so the method is not terribly complicated. I give you energy levels, right? If the energy level is above the potential energy, that means motion's possible because the kinetic energy plus the potential is the total energy. So if the total energy is less than the potential, that means kinetic energy is negative, which is impossible because kinetic energy is 1/2 mv squared, which is non-negative. So E1, no motion possible. E2, no motion possible over here and also in here, but right here and here there's a little motion possible. And that gives me these little loops down here and that little divot right there, all right? Energy 3, I get this guy right here, all right? Energy 4, I get this bit here. And I get this little loop over here and this guy over here. Trajectories up here are moving to the right. All the trajectories down here are moving to the left. And wherever there's a critical point in the potential energy graph, there's going to be a corresponding either like critical point at the x-axis or a horizontal tangent if we're above the critical point, because these points are places where dv dt is 0, right? So anyway, there's a clear pattern that goes on here. And any questions about this? Now, the whole point of this is that we can qualitatively understand possible motions for a system, even if we couldn't actually find, the explicit solution to the problem. Like if we know the potential energy, we can make an energy diagram and analyze it. Now, if we were not in a, in-class format, we could pull out p-plane, right? We could look at the p-plane diagram for the differential equation, and we could actually numerically generate solutions and understand things from that perspective, right? Here is another one. So, yeah. Hooray. Okay, so, all right. You guys have any questions while I'm poking around in here? I think I've pretty much talked about everything I have to say about inverse transforms and transforms, as far as I can think of. We should probably go back to mission 3, right? Because mission 3 is also informing. Yes, sir.
I was going to say, I already have a note card written out for test number 2. Can I print out one of those sheets and bring the note card? Or should I just copy it all onto one page?
Copy it all onto one page. Yeah. You can photocopy the note card and just literally paste it on the thing or scan it. Scan it and then I would scan the note card and then you can just cut it and put it onto the thing. I don't know. There are many ways. But I do one page of notes just to have a rule. All right, so this was mission 3. And what did we go over in mission 3? Oh man, it's been a minute. I almost forgot about these. That's right. I got to test you guys on series solutions. Oh no. I don't have to, but I will. So there are two kinds of problems to be aware of, generically speaking. The one is find the first three terms, something like that, right? The other is find the complete power series solution. Obviously, find the complete power series solution is more troublesome, and you need to use the sigma notation, right? But we can get to the solutions here. I don't really have much to say about those. We talked about them before. Basically, the deal is assume that your solution is the form of a series, plug it in, and then work out the equations that relate the coefficients. We should always find two infinite families that are related, right? Because if we're talking, at least we're talking about second order problem, we need an initial position and initial velocity to solve the problem. Beware, every so often I throw a curveball and I give you a problem that you actually don't need to do the substitution stuff for. Like, check this out, right? This problem I solved with what? I mean, this, in some sense, this is a better solution, right? But because I asked for a series solution, I turned this into a series solution, right? This is pretty silly, but that is way easier, I think, than what's down here. But anyway, of course, this is actually what I'm more kind of expecting you to do on the test if I was to have a problem like this, which is to plug in the series solution and work out the recurrence relation on the coefficient, and then kind of tinker with it until you can find a pattern. In this case, it happens to be 1 over k factorial for the even terms, and it's 0 for the odd terms, which of course brings us back to where we got to the other way, namely e to the x squared. Yep.
If you did something like that on the test, would you be allowed to do the shortcut version?
Oh yeah, yeah. If there's a shortcut possible and you take it, then I probably get bonus points, if anything. Yeah. Showing me that you understand series in some kind of deep way, and the interplay between the functions which they represent is a net positive to me. All right. So anyway, these require careful thinking and, attention to detail. In other words, don't be up until 5 in the morning the day before the test. If you want to have a shot at these, you need to be fresh, right? There's just no way about it. Anyway, and also, I do give significant partial credit if you, had like notable markers in the solution process, right? Number 1, starting with a series. Number 2, finding your way to something like this where you have like the general term and any exceptional terms out front, right? Understanding that implies this recurrence relation. Those are sort of milestones on the journey to the complete solution, right? So getting to that point is a significant partial credit event. And then past this point, tinkering, that's the ultimate best solution is finding the best formula, right? But that doesn't mean you can't get significant partial credit from getting something beforehand. Now, if I ask for the complete series solution and you just give me like, a couple and then plus ... I'm not going to give you a lot of credit, right? If I ask for the complete series solution, I am looking for you to meaningfully interact with the sigma notation. All right? So plus ... will get you partial credit, sure, but not a lot in that problem. Now, anyway, the other thing, of course, to be aware of is you do need to know series expansions for all the elementary functions that you know and love, like the exponential, the sine, the cosine, and elementary geometric series stuff, right? All of these things you ought to be able to do. Those are kind of gateway steps to solving the problem. If it's an inhomogeneous problem, you notice that like the math works out a little bit different. Like we've got two different things going on. You've got the pieces that are proportional to the constants, but you've also got the other piece appearing, right? And the other piece which is appearing, that's going to kind of correspond to the particular solution in your solution as it happens. But all right, I do oftentimes ask a question like problem 54. Don't give up on this question. This problem is actually really easy. You just have to understand what's being asked and how it works. The theorem is simply this. If I have a differential equation, right? The solution, the domain of the solution is going to be as big as it can be such that it doesn't go over a singularity. Now, the way the solutions to a power series solution works is it has to be centered at its center, right? So once I write x plus 2 here, that fixes the center of the solution at -2. -2 is in the domain no matter what else happens. Because if I plug -2 in here, I get 0. And 0 converges because it's just 0 plus 0 plus 0, right? So -2 is in the solution if I write something like this. So I know that my solution starts at -2, and then we have to take a complex perspective, it turns out, and think about the disk of a particular radius in the complex plane like that. Now, looking at this, I have a singularity at 0, and I have a singularity at, completing the square here, -1 plus or minus I. So that puts, singular points here and here. It's fairly geometrically clear that these are closer than 0, right? 0 is 2 units away from -2, whereas these are, square root of 2 away. So they're a little bit closer. And we run into this guy the same time we run into that guy. So they appear symmetrically. I can't go past that. That's the largest radius I can manage centered at -2. And for that reason, that's the largest open interval of convergence, -2 plus or minus root 2. So the way you do these is simply identify your critical points. The critical point is going to be something that makes the y prime prime term drop to 0 if it's written like this. If it's written the other way, so y prime prime is just on its lonesome, you're looking for things that are divided by. Any place where you have division and the denominator is 0, that'll make a critical point, right? And you just plot all the critical points in the complex plane. You plot whatever your center point is in the complex plane, and then you simply look for what's closest. Whatever's closest informs your radius of convergence, and you do center plus or minus the radius. That's the largest open interval of convergence. That's how you do it. This is just a fun calculation, right? We can understand e to the I theta from plugging it into the Maclaurin series. So that was fun. The copier is doing some weird stuff here. I was trying to get it to zero out the background stuff, and it's done some kind of I don't even know how to describe it. some funny stuff. Okay, so here, this is just a plain old sigma algebra notation question. I can test your ability to do sigma notation calculation by asking for a complete series solution, right? But another way for me to test on that is to ask a question like this, right? Which is kind of more focused on that particular skill set, yeah? And the basic idea is simply that you have to match like coefficients, right? So this is even, right? And if we think about e to the x and cosine, there's different ways to get even. So e to the x is cosh plus sinh, and this ends up being, as you can see, this and that. So even power series come from even functions, as it turns out. So this cosine 2 term and the this term, these are going to go into the even term, and then the others go into the odd, and even and odd are separate, they don't overlap, so we get these formulas, and that's how that goes. But the basic idea is that given a 2 power series, we can equate coefficients of power series. That's the underlying concept here. So these are just basically review of calculus 2 geometric series integration stuff, so I'm going to skip past here. All right. So here we have a system of differential equations. So we know the method, I hope, at this point, right? We write down the matrix, calculate the eigenvalues, find the eigenvectors. E to the eigenvector is an eigensolution, right? This is a 2 by 2 system, so we need 2 solutions for our general solution. And indeed, we have it. Yay. Problem 47. Here we're talking about, a fundamental matrix, and B is a square invertible matrix. I'm supposed to show that X times B is a fundamental matrix. So first of all, I differentiate it. Of course, b is a constant, so it differentiates to 0. And that gives me dx dt times b, which of course is ax, since it's a fundamental solution matrix. And so lo and behold, I find that the derivative of xb is equal to a times xb, which is to say it's a solution matrix. Now, to say it's a fundamental solution matrix is to say it's invertible. To check invertibility of xb, we simply take the determinant. The determinant of the product is the product of the determinants, but these respectively are given to be non-zero. Yeah. What? What's this? Well, how did I get to this? Well, 58. Oh, that's the old numbering. I'm sorry, guys. That's problem 58. Oh, this is just a bonus solution, but it's a good solution. It's a good problem to look at, nonetheless. We did talk about this in class, though. Like, we did have this discussion about if you have a solution matrix and you multiply by an invertible matrix, we get another solution matrix. I did derive this in class. It's just it's been a homework problem in a previous year. So, my apologies. Fair point, though. That was not technically a mission 3 problem. It is within the scope of the course, though, because I lectured it before. Anyway, so here you're supposed to calculate. It's relevant to this as well, because e to the part of the reason I left it is because of this. To calculate e to the ta, given that a, we can basically use this general theorem that says e to the ta being a fundamental solution matrix can be written as a constant invertible matrix times a given solution matrix. Now, the given solution matrix I have in mind is simply formed by concatenating the 2 eigensolutions we just found for the problem, right? So this x of t is simply the 2 solutions I just found on the previous page put into a matrix. And the theorem says that e to the at we can calculate from x of t times x inverse of 0, but x inverse of 0 is this, as it turns out. And when I multiply them, I get this. And so there you go. This is the matrix exponential, which is a kind of sneaky calculation, right? So we can calculate the matrix exponential if we have a solution matrix by doing this little trick. What's the other way to calculate the matrix exponential? You just calculate I plus ta plus t squared over 2a squared plus t cubed over 3 factorial a cubed, and just calculate that infinite series, right? That seems harder, right? Yeah, I mean, Jordan form's helpful if we knew what that was. But now here's another problem. This one, we find eigenvalue 2 repeated, right? And that gives us 1 eigenvector, and we get 1 eigensolution, hooray. But that's not enough, so what do? We use the matrix exponential. We look for a generalized eigenvector of order 2 in this case, which gives me this equation, right? I solved that. It gives me u2 is 0, 1, all right? And then I consult the magic formula, and I multiply u2 times the magic formula, and out pops u2 plus tu1, all right, which gives me this. And so my second solution, I first have the eigensolution, then I have the generalized eigenvector solution, all right? Now, as a point of order, if I have a problem like this on the exam, you don't have to recreate the wheel. Like, you don't have to do all of this. It's perfectly acceptable for you to go, u2 is a generalized eigenvector, satisfying this condition, therefore the solution is e to the 2t times, u2 plus tu1. It might be smart to kind of like record this as a result, that if we have e to the at times u2, we get e to the 2t times u2 plus tu1 in the case that u2 is that u2 satisfies this condition, right? I mean, you'd like to understand the derivation, because if I renumber things or something, you won't get hung up on it, but anyway. The larger point is, if we don't have 2 eigenvectors, right, for a 2 by 2 problem, then we need to look for a generalized eigenvector of order 2, all right? The other possibility, of course, is that we have a complex eigenvalue, like here, in which case we get a complex eigenvector